leaf modeling and Eclipse version 18. We are thrilled to have Anne Van Eyck with us, and I will give you a moment to review the Varian safety slide. As a reminder, all products and features are not available in all markets. And Anne, I will turn it over to you to get started.
Okay, thank you. It is my absolute pleasure to be allowed to talk to you about the new MLC model, abbreviated by the enhanced, so the enhanced leaf model is abbreviated by ELM. The original idea of this model was to improve the dose calculation, but also to make the whole MLC parameter optimization in Eclipse more streamlined. And on a side note, originally, as I am not English speaking as my mother tongue, I thought ELM was another boring abbreviation until I realized that it is actually the name of a tree, and a tree with a very distinctive leaf for that matter. So I have changed my mind, and I now think it's a very creative and appropriate abbreviation. So it is not my work that I am presented. This is the result of a particularly enjoyable team effort during strange COVID times with myself and Antti Kulmala from the Helsinki University Hospital on the measurement and testing team, and Ronan, Juha, and Ari from the Varian algorithm development team in Helsinki on the theoretical side. All of them delightful personalities. But first, I have to show you this extremely interesting slide about disclosures and stuff. There it is, done. So let's move on to what we are really here about, dose calculation. So when we talk about dose calculation, it sounds like a single thing, but it is actually composed of multiple components, right? If you want to do a dose calculation, right, you have to characterize all three components. And the first part is you need to know what is coming out of the accelerator head, the projectiles, so to speak. Secondly, the target, you need to characterize the target, which is the patient, the phantom, the imager. And then if you want to have a precise dose calculation, you need to be able to model the interaction between the projectiles and the target. This is very important to keep in mind. The precision with which you will get a dose calculation depends on the precision with which you can model all three of them or characterize all three of them. And so it all begins with the precision with which we can model what is coming out of the accelerator head, the projectiles. This is precisely what Eclipse tries to do in beam configuration. When you input your beam data, the model tries to deduce how many particles, photons or electrons, are coming out of the large open beam. And what is there for each pixel, it tries to decide what is the particle intensity and what is the particle energy. If you know that, you have done your open beam model. You have configured your so-called open beam model. Of course, in reality, we hardly ever use open beams. There is always JAWS or MLC in there. And in order to model the projectiles that actually fall onto the patient, these need to be taken into account. And Eclipse does that by calculating the so-called fluence. The fluence actually determines which of the original large open beam particles make it through. So if you have a fluence 1, it means all go through. If you have fluence 0.01, it means 1% goes through. And under the JAWS, for example, nothing goes through, so the fluence is set to 0. Now, when you have an MLC, a static or even a dynamic, it's a little bit more complicated than that. For a dynamic MLC, the fluence will be calculated for every control point and assuming linear movement in between. So the values are not that simple, but the idea remains the same, right? And the modeling of this fluence coming through to the MLC, that is actually the subject of this presentation, because the precision with which you can model that will strongly affect your dose calculation, right? Knowing that, let's take a trip down memory lane, to see how this little baby has matured over time. In the pre-IMRT era, when we used MLC as simple block replacement, really, nobody bothered about the specific shape of the leaf tip. In the open area, the fluence was simply set to 1. And in the MLC shielded area, it was set to a fixed transmission factor. And under the jaws, it was simply set to 0. Simple as can be. And the MLC transmission was simply defined as the ratio between a closed MLC field and an open MLC field. So fixed jaws, closed MLC, open MLC, the ratio is the transmission. As I said, nobody bothered about the rounded leaf tips. So that means that, for example, if you had closed leaves in a field, the dose would be ignored there. The dose coming through the leaf tips would be ignored. Now, this could no longer be ignored when IMRT came, of course. So when IMRT came to life, the dosimetric leaf gap parameter also came to life. In theory, this parameter was supposed to model the penumbra shift due to the rounded leaf tip design, right? So it actually opens the fluence in the x direction by half the DLG value, and where the leaves were closed, of course, it is as if you have an open field size of DLG width. In theory, penumbra shift due to rounded leaf tip design, but in practice, it was that plus the 0 leaf gap, because when leaves are closed, how close are they really? That depends on the variant engineer, on the calibration procedure, and on the history of the center also. So this is not the same for all treatment units, and it requires input from the user. For IMRT fields, these fields by nature are rather synchronous in movement, so that the leaves go from left to right. And because of that, tongue and groove really had little impact on the dose calculation. There was hardly any tongue and groove present. But when rapid arc came, this totally changed, because the rapid arc movements, as you all probably know, are more visually chaotic, with leaves constantly changing direction, going from left to right. So tongue and groove needed to be modeled, and it was added to the MLC fluence model. So basically, in the y direction, the effective field size was reduced by typically about 0.3 millimeter, modeling the part of the leaf sticking out, making the tongue and groove design. And that's it. That is actually the MLC model that is currently in use in most of the clinical centers and has been in use for quite a while. But over time, things have been changing. While we are still using the same MLC model, the optimizer has changed dramatically over time. It has gone from this simple optimizer in the very early Eclipse IMRT modules to the much more sophisticated optimizer we have now. And treatments have become more and more complex because the treatment optimization has increased. Clinicians have ever more demanding goals on organ sparing. Volumes get smaller and smaller. Heterogeneities are calculated more correctly, and they are also more present. And we have more and more tools that allow us to push the optimization really to the limit. And on top of that, a new treatment unit was born, the Halcyon with the dual layer MLC without any jaws. And as if that was not enough, we have grown so accustomed to having excellent gamma criteria that we want to keep these equally good scores no matter how much we push the system and how crazy we go. So trouble was maybe to be expected, but let's see how good was this simple model, or how good is the current model actually? Well, it is mostly very good actually, surprisingly good. I've had almost always very good results on the dose calculation and measurement comparison for large fields, integrated boost fields, medium fields, and even for very small hyperarc lesions. So mostly very good. The problem, of course, lies in the almost, because sometimes results are okay, but not perfect. Little discrepancies start to pop up. You know, the absolute dose level might not be exactly what we hoped it would be. And sometimes it's in the lower dose areas that we do observe deviations. So these are clinically acceptable, but not perfect. And then sometimes we really have results that we would have liked to improve. It is very difficult to see, to define where the problem comes from, right? Or to define a tendency. We do see a tendency that for very highly modulated deliveries with very small average MLC openings and therefore high MU per gray, results deteriorate. So it is only natural that we want to improve the agreement between measured and calculated dose for plans with this increasing complexity. But it is not so easy to know who to blame, because there are many possible suspects, many possible culprits. So people who know me and who have worked with me, they will know what's coming, because I can go on and on about this, but it's very important, so please bear with me. When you have done an optimization, say a rapid plan, a rapid arc, hyperarc, IMRT, whatever, imagine you have a plan prepared. From this ensemble of leaf movements on the TPS side, on the TPS side, affluence will be calculated from this ensemble of movements, and using this fluence, the dose calculation will produce the dose distribution in the patient using the algorithm of your choice. On the delivery side, the plan is sent to the record and verify system, and then it is the responsibility of the accelerator's control unit to deliver the planned treatment with precision. Imaging is supposed to check that the patient positioning and the patient anatomy match the one on the planning CT, and if all goes well, these will agree. Right? If we do report, if they don't agree, any of these above arrows can be the cause of trouble, right? And if we say that we observe discrepancies between measurement and calculation, we actually usually refer to QA systems, because we can't really measure in a patient. So we are saying we're observing deviations here, but adding a QA system adds additional arrows to the whole circle. So it's difficult to know where the problem lies if we find a problem. But there is one thing we can all agree on, that is small is trouble. Small MLC openings challenge the fluence calculation, the precision with which it can be calculated. It presents a challenge for the dose calculation. It demands high precision of the machine delivery. It's very highly demanding on patient positioning. And if that's not enough, it's becoming more and more difficult for us to measure precisely. And last but not least, the gamma criteria we love so much, they are becoming really quite useless when we are dealing with small fields. So small is trouble, and if we see discrepancies between measurements and calculations, it is best to tackle one arrow at a time. Get all of them optimized. And the arrow we are focusing on when we improve the MLC model is the fluence calculation. Do keep that in mind, right? So, this being said, let's go back to the simple leaf model that has been used up till now. This model actually presents the MLC as a homogeneous, thin filter, if you wish, that either attenuates the beam by a given transmission value, or it lets the beam go through its opening. The transmission is usually measured on the beam axis, right, and then applied everywhere. And for the beam opening, we need to set the dosimetric leaf cap. The dosimetric leaf cap, as I mentioned before, is actually the mechanical leaf cap, so the zero leaf cap plus the rounded leaf tip penumbra. This was modeled by the DLG, which means that when you have a leaf cap of a nominal opening of delta x, or MLC opening of opening delta x, then it will be modeled here, then it will be modeled in the fluence calculation as delta x plus the dosimetric leaf cap. And this fluence representation is really what it looks like in the current model. Notice also that this means that regardless of where the opening actually is, it can be as far off axis as you wish, the shape of the fluence will be the same, right? Regardless of the off axis distance. Right? The enhanced leaf model does not look at the MLC like that anymore, no longer a thin, homogeneous, flat filter. It now tries to take into account the actual shape of the leaf, right? And through ray tracing of all the beamlets, it will determine how much MLC material this beamlet has actually encountered. Right? So the leaf transmission is still modeled on the beam axis, but using this value measured on the beam axis, all other areas of the MLC will then be modeled accordingly, depending on how much material each individual ray encountered on its path through the MLC. This means inherently that the rounded leaf tip is included in the model, because the rays actually transfers the leaf tip, and the fluence that's coming out, is determined by the shape. So there is no more need for a dosimetric leaf cap. There is, however, still a need for a mechanical leaf cap, because, as I said, not all MLCs are calibrated in the same way. So you have to have this mechanical leaf cap, which means the zero gap of the MLC. When an MLC is closed, how closed is it really? And that value will still be is still required to be entered by the user, but I will come back to that later. Let's have a look at the consequences of this model in the fluence. Well, first of all, you can see that where the very straight block shape we had in the old model is no longer present in the elm. We now have a very rounded edge of the opening in the fluence. And secondly, we have this area of the leaf tip where we have a lower transmission, because in this area there was the hole of the screw drive is not present, so the ray encounters more MLC material, so it has lower transmission. And thirdly, it's a bit less visible, but still present. As we move further and further off axis, the transmission value decreases compared to the on-axis value, because the path length through the leaf increases. So again, longer path length, more MLC material. And this is what the fluence will look like with the new model. In the direction perpendicular to the leaves, this is not shown in this graph, but I will come back to it later. The model also now models the different leaf zones. So for example, difference in transmission between the 2.5 millimeter leaves and the 5 millimeter leaves. You will see that in a second. So when developing and testing the enhanced leaf model, Antti and I had to come up with a set of test fields that met the following requirements. We needed test fields that specifically highlighted the flaws in the current simple MLC model, and we needed these for all MLCs. And we also needed to minimize our measurement uncertainties, because when discrepancies between measurements and calculations are observed, these algorithm developers up north, they have a clear preference for blaming it on the measurements. So we needed to make sure that we were covered. For that reason also, when doing film measurements, we never, ever, ever rely on film alone. And we needed to test multiple beam energies and multiple treatment units. So we did many tests, but in the end, simple is best. So the tests I will be presenting to you here are all in a simple solid water setup, SSD 90, gantry 0, collimator 0, with a single ion chamber. With ion chamber arrays, we used the PTW 1500 large field detector and also the 1600 SRS detector, and we used film. Right? Now, don't go thinking that you need to redo these measurements. They were developed for testing and development purposes. If you want to redo them, feel free to do so, but it is not necessary. I just thought I'd mention that. So let's have a look first at the most simple test of all, the off-axis transmission modeling. This is a very simple static MLC field with a closed MLC with the isocenter here, so it's a very asymmetric field. The X1 jaw is as asymmetric as the over travel will allow. If we look at the profiles extracted from the measurements, you can see the blue squares are the Octavius 1500 data points. The circle is the ion chamber, single ion chamber measurements. The original model, of course, calculates this as an open field, but with only the transmitted dose, whereas the L model clearly shows the improved modeling of the leaf tip, where the missing hole of the screw drive is present, and it even shows the decrease in transmission as you go off axis, better than the original model. Do keep in mind that the transmission measurements are always noisy and scattered measurements because of their nature, but still the improvement is quite obvious. And as I mentioned before, in the direction perpendicular to the leaves, ELM now models the different overall transmission between the central 2.5 millimeter leaves and the 5 millimeter leaves towards the edges. So this is also a very clear improvement, readily seen in a simple transmission measurement. So now we go to the impact of the rounded leaf tips. We first wanted to do a measurement with relatively large fields, so we needn't worry about small field issues. So we made a plan with multiple simple static open MLC fields that together cover a larger surface, much like wallpaper covers a wall, hence the name. And we did these tests on the true beam and on the halcyon. On the true beam, we programmed some slight overlap between the different static fields to minimize those peaks at the junctions, right? So we can see from the red line, which is again the original MLC model, the red line actually shows near perfect junctions, whereas the measurement does not show this at all. In the measurement, we see bumps, 2 bumps around a central peak at every junction. And these are the result of the actual leaf tip shape. And the L model reproduces this very well. At the halcyon, the impact is quite different, whereas the original model also expects a nearly perfect junction. Measurements show that this is not at all the case. We see clear dips at every junction. And the L model agrees very well with what we see with the measurements. So these simple fields that can easily be reproduced or tested if you wish are already very motivating. So when large fields work well, let's go to narrow strips. So here we do go into narrow MLC openings. Again, for the high definition MLC, we have 3 millimeter strips on axis, and we move them further and further off axis. I think 4, 8, and 12 centimeters. Don't remember exactly. It's similar for the halcyon, right? 3 millimeter wide slits. You can see on the TrueBeam that the height of the peak is actually not so badly modeled. The height of the peak is quite okay, and the central peak is also rather well modeled with the original MLC model. But as the peaks move further and further off axis, we see clear discrepancies coming up in the low dose area of the peak, right? That's the typical phenomenon on the TrueBeam MLC. On the halcyon, quite different. In the low dose areas, there is no noticeable deviation between measurement and either of the MLC model calculations, but there is a significant impact on the height of the peak. So the original MLC does not calculate the height of the peak well. I think it's about 30% difference. But with the new model, we are within 3% agreement on the height of the peak. So these imprecisions in the model, there and there, they are now in static narrow slits, but they are expected to accumulate into serious consequences when you do dynamic delivery with such MLC openings. So that's the next part. So the next step in the testing goes to dynamic delivery with narrow openings. What we have done here is we have what we call made a zebra crosswalk test. It's probably most visible here. So we have painted fluence strips of 2 centimeters wide, but these fluence strips are delivered by 3 millimeter sweeping gaps for the high definition MLC, and I think 5 millimeter sweeping gaps for the halcyon. So let's see if the results are consistent. They are very consistent. The central zebra stripe, for that one we have about 3% difference between on the dose on the beam axis. This could still be considered a clinically acceptable deviation, I think. But as we move further and further off axis, the discrepancies really increase, I think, to up to 15% for the 12 centimeter off axis stripe when using the old model. I clicked on the wrong model, the old model. That's 16% difference. Elm does brilliantly. Elm reduces the discrepancy, I think, to within 1% for all of the stripes. Magnificent. On the halcyon, the result is again not the same. The impact is not the same as on the TrueBeam, much like it wasn't in the static stripes, but we also see a tremendous improvement for all of the, almost equal for all of the stripes. The overdosage or the over estimate of the dose that was observed in the stripes from the static test is equally visible in the dynamic one, and ELM makes the agreement to within 2% or 3%, I think, which is much more clinically acceptable. So in the halcyon, these deviations are mostly due to the very synchronized movement of the dual MLC. Yeah? This is very important to keep in mind. So I do hope I haven't bored you by showing you all these detailed data. I was afraid I would, but then I figured you would rather see the data than take my word for it. If you have drifted off and you regret it now, you can always read up on these tests in the publication. This publication discusses exactly the tests that I have been showing to you. Do keep in mind that these tests are specifically designed to highlight the problems. They are so-called drama queens, but they can help us predict the expected changes in clinical plans. So let's have a look at what we expect and see if our expectations come true. For the TrueBeam, we now expect an improved dose calculations for plan with a very high degree of modulation, so with very low average MLC, small average MLC opening. We expect improvement on axis, but even more so off axis, right? For the halcyon, we expect improved dose calculations for plans with narrow MLC caps, especially for plans that have both leaf tips of both MLC banks relatively aligned. That's the expectations. Now let's go back to these clinical plans for which the QA did not fill us with ultimate joy. If we recalculate with the new model, we do see that results get quite a bit better, right? Here as well. In these cases, all improvements are observed in the high dose region, but where we had low discrepancy in the low dose region, also see that ELM produces the measured profile much better, right? So we are quite happy with the improved dose calculation, and we assume you're going to want to use it in clinic for that matter. So you want to know what you need to do to actually take the model into use. Well, while the improved dose calculation in version 18 was the original goal of the ELM project, as an additional result or as an additional goal, the MLC parameter input in Eclipse was also changed to make your lives easier during configuration, you know, to get rid of all this mystical and empirical MLC parameter optimization. But you still need to provide Eclipse with input. What will you have to do? Well, in version 18 for the halcyon, of course, you don't have to do anything because it's pre-configured. Physicist, no work for the physicist in addition. For the TrueBeam, not so much, right? Because you still need because all MLCs are a little bit different, you will still need to provide transmission data. Now, as a transmission is a dosimetric parameter, it is quite natural to provide a dosimetric measurement. We will just use what we have always used. A simple solid water setup, a large enough ion chamber, isocentric setup, and you make the ratio of and you measure a closed MLC and an open field. Simple as that. The leaf cap, now, because it doesn't take the rounded, because you don't have to model the rounded leaf tips anymore, it has, strictly speaking, become a mechanical parameter. So, in theory, it could be a physical measurement of the actual leaf calibration, a physical measurement with a feeler gauge, for example. I never liked the idea But the Finns insisted that I try it, and because I really like the Finns, I did buy a feeler gauge online. As you can see, it arrived on the 23rd of December. So I had the brilliant idea of performing the measurements on the 24th of December, because on Christmas Eve, the treatments stop sooner, so I thought I would have some machine time. I will not share on the internet what happens on the 24th of December, but let it suffice to say that I was late home for Christmas, and I will never, ever, ever do feeler gauge measurements again. Not only was it a fiasco on a practical side, also, at least I was able to perform the measurements eventually, and as it turned out, they were by no means accurate enough. So we are not doing that. Instead, we are going to use the sweeping gap measurements we have always done, because we already know that these are the measurements that are mostly sensitive to the MLC calibration. And you all know how to do these. What has changed now is that the beam configuration workspace will automatically deduce the mechanical leaf gap from these measurements for you, so you don't have to process them anymore. Right? So imagine now that you will have your upgrade to version 18 coming up. It is best to be prepared. This is true for life in general, but for the upgrade in particular, because you will have to have the measurements at hand when you actually configure your system. In the Eclipse 18 version, the MLC parameters that you use to put in RT administration will no longer be used. If it's confusing to you that they are there, you can delete them, right? You will now have to input them into beam configuration, right? And in order to be able to do that, you will need to have the measurements, the results of the measurements ready. This has been prepared for you beforehand, and it is available on my variant. So DICOM plans have been made for you to import, and a procedure has been made for you to follow. I helped writing the procedure, so it should be practical and concise, but I haven't looked at it since Varian edited it, so I'm not sure if they haven't added a lot of exclamation marks and warnings and stuff. So I think it might be a good idea to just practically go over the steps you have to take and demystify the whole thing, right? So DICOM plans have been made for you. You can just import them into your Eclipse system. They are made for 6 MV beam and for both MLC. If you don't have a 6 MV, they are also there for 8. Just import and you will see whatever comes up is your energy. Then you just go to plan parameters, you add your favorite tolerance table, you copy paste the plans for as many energies as you have available on that treatment unit, and then should the MUs have disappeared when you change the energy, just set 500 MUs back for every field. Planning approved, and you are done. Yeah. When the time has come and you feel like it, you can go to your TrueBeam and perform the measurements. So as I said, perform these before you do the upgrade. You just put on your solid water or your small water phantom, put in a reasonably large chamber, put your chamber at isocenter, and just make sure that it is perpendicular to the leaf movement, right? And then you just deliver the fields, all of the fields that are prepared. You write down the measurement in nanocoulomb. There is no need to make sure your absolute dose output of the machine is perfect. Not at all. These are relative measurements. So just write down the nanocoulombs and you are all set. When you finally have your Eclipse 18 in front of you, you go to beam configuration. Of course, as always, you will have to recalculate your open beam data and all your accessories first. Do that first. When you have done that, by a right click on the beam, you add a new add-on. Right. And then you select the Elm multi-leaf collimator and you select the ID of your MLC material. Usually there is only one ID available there, so there is not much choice, don't worry. If you have some choice, go and check in admin which the ID is that you have to select. Once you have done that, you can just enter your measurements into the orange boxes. There they are. I just manually entered them. And then you right click on the Elm multi-leaf collimator and you calculate beam data. That is all you need to do. And the system will come up with the leaf transmission factor for you and with the dosimetric leaf gap. Yeah. So a little note on terminology here. The leaf cap, the so-called mechanical leaf cap, is now still called the dosimetric leaf cap because it is deduced from dosimetric measurements. I don't like this. I have fought a battle. It's a battle I have lost. I think it's confusing because you use the same word for a different entity. So it's confusing if you don't know, but now you know, so you should be unconfused. Have a look at the values. The leaf transmission factor should be easy to check because you can just simply calculate it yourself from the ratio of the transmission field and the open field. And the value you have over there is the average of A and B bank. The dosimetric leaf gap, or the mechanical leaf gap, as I prefer to call it, is usually very close to zero and often slightly negative. You can do one check because it is now a mechanical quantity. The leaf gap you obtain for different energies on the same machine should actually be very similar. They are mostly not identical because there's small variations on it, but check between the different energies and you will see, if all is well, that they are within 0.1 or 0.2 millimeter identical of each other. But also do have a look at the comparison of the measurement, the measured and calculated points. Right? You should have a visual match between your measurement points and your calculated points. Right? If you have this visual match, usually all is well. If it looks somewhat like this, that's not good. This is not looking good. That means you have entered a wrong value at some point somewhere. Do not be embarrassed. This can happen to anyone. Don't ask me how I know. So then just go back over your values and correct it, right? If you have finished your configuration of your AAA or Acros algorithm, then you still have to enter the Elm parameters in the optimizer algorithm. So in the PO, this similar procedure, just add a new add-on, select the Elm MLC configuration. But now you don't have to enter your measurements anymore. It will just allow you to copy in the leaf transmission you obtained from your algorithm of choice and the leaf gap from your algorithm of choice as well. Just manually copy them, simple as that. Check for typos and approve your algorithm, and you are done. Take a moment to enjoy it. This is also a general advice in life. Right. Have we now achieved perfection? Probably not. Perfection is very difficult to achieve, but we have achieved important progress. First of all, the MLC parameter configuration has now been automated and standardized, and I personally think this is a very important step forward, right? Because it will it liberates you from the mystical and empirical transmission and DLG parameter pair optimization. And on top of that, we have improved the dose calculation. We have made it especially more robust in case of extreme optimization. And as we move more and more to extreme optimization, I think this is very important too. Does that mean we are there yet? Of course not. There are further challenges. I notice, or maybe you notice it too, that in small fields, small lesions, highly modulated, I still see some systematic, almost systematic discrepancies of 2% in many cases, especially when the lesion is on the beam axis. And there is the hypothesis that this could possibly come from the tongue and groove model. So there is a question if some refinement of the tongue and groove model could further improve this, or maybe source model refinement is also desirable. But I think it is also time for us to realize that as we improve calculation ever more, the problem is that we have achieved now a precision that comes in the area of the measurement imprecision. So our measurement imprecision has become of the same order of magnitude as our dose calculation imprecision. And this means that for me personally, I think we have an urgent need to standardize or benchmark our QA equipment so that we make sure that we don't go barking up the wrong tree, because if we are brutally honest with ourselves, for very small lesions, 5% inaccuracy on a dose measurement is not all that unusual. It can be even more. So I think with this little note of self-reflection, this is a good moment to finish and to share with you the secrets behind the success of the new MLC model. Because I think it is very important to realize that once something is done, it always looks simple. So I would really like to end this webinar by thanking the Helsinki algorithm team who have made this all new model possible. Right? They have improved the dose calculation for you. They have made it easier to configure your MLC parameters, and they have provided me with intellectual challenges and much joy during our numerous video calls. So a big thank you to them and thumbs up for their work. And with this, I will give the word back to Baron.
Thanks, Anne.